Hi, everyone. We're honored to kick off our seminar series on analytical sociology with today's guest, Joshua Becker. Joshua earned his PhD in communication from the University of Pennsylvania in 2018, and currently he is an assistant professor at the University College London School of Management. His research focuses on collective intelligence in general, and more specifically, he studies how teams, organizations, and societies can optimize their decision-making. Several of his papers published in prestigious journals, such as Science, Management Science, PNAS, as well as Harvard Business Review. Before giving the floor to Joshua, I would like to thank everyone for joining today's seminar, and would like to everyone, especially joining online, to keep their microphones turned off during the seminar. Joshua will accept clarification questions or any questions as we go along, as I understand. So either speak up or raise hand or chat, the chat function if you have any questions. So without further ado, it's a great pleasure to have you here with us, Joshua. The floor is yours.
Okay, hello. Yeah. Thank you so much for having me. Just want to give a couple quick notes of introduction on top of that. So all of that is true. Also, so I have chronic congestion, so I always wear a plaster on my face. Sometimes people ask, it's very embarrassing, but I don't care. Also, yes, I did my PhD in a communication department. My primary advisor was a sociologist. My secondary advisor was a sociologist. My other one, I was close with all my advisors, was a political scientist. Then I did a postdoc in a management school. So I'm just a little bit confused about what, disciplinary boundaries really mean in terms of social science. Also, now that I am thoroughly ensconced in the management world, it means that I will feel very strange if I get to talk for more than 5 minutes without interruption. So I empower you all. Actually, can I just have a quick volunteer? Does anybody want to raise their hand for something?
Volunteer for what?
Okay, wonderful. You now have you're specifically encouraged to interrupt me mid-sentence at some point with a question. Totally fine. Okay. So yeah, please do feel free to just talk throughout. And then I also want to just acknowledge this is my first time giving a talk in person in a while. I was even just giving a talk on Zoom last week to the point where I was briefly confused about what I'm supposed to do with this clicker, which my life used to revolve around. So, okay. All right, without further ado, I'm going to get into the science of things. So I'm very interested in collective intelligence, and particularly research on the wisdom of crowds. So the main question that interests me, or the one I'm going to focus on today at any rate, is how can we maximize group belief accuracy? And I'm saying belief in the broadest sense. So you can think about this in terms of forecasting. I'm going to narrow this down and use the term numeric estimates for the rest of this. So the thing about this is research on the wisdom of crowds is motivated by the observation, both empirically and theoretically, that you can actually get incredibly accurate estimates, numeric estimates, forecasts by asking a large group of people. Not only that, but you can actually get a more accurate estimate by asking a large group of people than any of the people independently. So we have a mathematical guarantee that the average estimate from a group is more accurate than a randomly selected individual. Mathematical guarantee. Okay, so that's the wisdom of crowds. I'm going to dig into that a little bit more in depth in a bit, but that's the basic idea. Ask a whole lot of people a question, you get a decent answer. So the kinds of questions that you can ask, now I'm going to get into more specific numeric estimates, things like, how many jobs will this policy create, right? How much money is some company we want to buy? How much is it worth, right? If I'm an investor, what's it worth? How much water is on the moon, right? I like to include this one because it's not always forecasting, right? There's also so-called nowcasting, which is estimating very hard to predict things. Or if you're, Bayesian, you can think about this in forecasting, which is to say, if we ever manage to measure this precisely, what will we find, right? So pretty much anything can be put in terms of a forecasting mindset. And I find that a useful way to think about it. Or, you're potentially hiring someone. So I used to hire for a customer service department where everybody was scored on how well they answered the phone. And I'm basically the person in front of me in the interview. All I want to do is predict what are they going to get on a score of 1 to 5 after 6 months on the job. Or you might be predicting, what's the publication feature going to be like? All right, so we're interested in any kinds of numeric estimates. That's basically my world, and that's everything I'm going to talk about today, okay? Now, as I mentioned, we have this great phenomena that you get the incredibly accurate answer by asking a lot of people, and that group average is going to be more accurate than any randomly selected individual. But this is kind of presuming this independent aggregation process, right? Going around and asking a whole lot of people separately, I'm doing the statistical aggregation. But what I'm really interested in is, what about the group processes? What happens? So you've got this great wisdom of crowds and statistical aggregate, and then I let people talk to each other, right? So what should I expect to happen? And not just for numeric accuracy, but for collective intelligence in general, we're kind of faced with a bit of a paradox, just strictly in the intuitive realm, and honestly, even in the more analytic realm as you get into it. On the one hand, communication can generate social learning, right? Other people know things I don't know, they have information I don't know, even just embedded in their estimate, right? Maybe there's a different piece of information going into the estimate. So on the one hand, communication can generate social learning. And on the other hand, communication can generate social herding, right? So we have these two kinds of processes standing in tension with each other, standing in opposition with each other. Okay.
Sorry, what's social herding?
Social learning, yeah, and I'm using this term really broadly, right?
I'm meaning the second one, herding.
Oh, social herding. I'm using this term broadly too, right? Both of these, and I want to acknowledge that I'm trying to tap into the intuition. So social learning, for example, is used by economists, particularly game theorists, in a very particular way, and it refers to a class of models with some behaviors. But social learning is also used in an education context. I can't say too much about that, it's not my specialty, but it's more about learning in a social context. And then when people talk about herding, it's this intuitive idea that basically we all end up thinking the same way at the end of the day. So, the idea being that social pressures lead to conformity. But I'm gonna unpack these concepts a little bit more analytically, right, as we do. But these are kind of the intuitions going into just the question of, should I let people talk to each other, or should I have them maintain independence, right? And there's actually, if you look back in the literature, I'll get into more of this in a few minutes, there's people kind of arguing for both. Okay, so then the question becomes, how can I actually optimize my group, right? So I had this intuition that there's a possibility for social learning. Can I somehow harness that and suppress the social herding? So one answer to how you can do this is that, well, it depends on the process that you're using. Okay, whether you'll get social herding or social loafing depends on the process. So we can imagine just people around the table having a conversation, right? So that's the kind of thing that just intuitively, and some of the literature from the 60s and 70s, people say, well, that's the kind of thing that's going to lead to herding, right? Because you've got this really direct face-to-face thing. I can be really persuasive, maybe pull the wool over your eyes, give you some kind of misinformation. We're all sitting around a table. We can all end up lumping together and end up believing the same thing at the end. People developed something called the Delphi method, which is an idea of saying, let's try to get the social learning without all the risks, right? So Delphi method is basically, I call it numeric exchange. It's a little bit more nuanced depending on who's implementing it, but basically instead of having a conversation, I'm just gonna write my estimate down on a slip of paper. You're gonna write your estimate down on a slip of paper. Someone's gonna calculate the average, and we're gonna share that. Or maybe you'll share the range, or maybe you'll share all the numbers. The idea is that by letting people see each other's numbers, you're sharing that information without the potentially detrimental effects that lead to herding. And again, I'm still operating very at the intuitive level right now. Okay, now the problem is that if you sit down and say, okay, well, how can I maximize group accuracy? Do I keep them independent? Do I let them communicate? And if I'm letting them communicate, do I let them talk to each other, or do I use this highly mediated kind of controlled process? If you look at the empirical literature on this, it's kind of all over the place. So there's some research that says, oh, have a conversation, people sitting around a table, that's the best way, right? There's some evidence suggesting that, oh, numeric exchange is best, right? So there's a couple studies. These include studies that actually directly compare numeric exchange and discussion, and some of them say numeric exchange is better than discussion. Some says numeric discussion is better than numeric exchange. So we're all over the place. And then there continues to be people who maintain that independence is best, right? Famously, James Surowiecki wrote this book, The Wisdom of Crowds, but also there's a group at Dirk Helbing's group. This is a very famous paper, How Social Influence Undermines the Wisdom of Crowds, right? So the evidence is kind of all over the place if you look at the experiments. So my answer, yes.
You asked a question, so I have one. So I have been confused. So why is it important to get the estimate from a group? Because when you talk about it, it sort of sounds as if it assumes that there is like a ground truth
Yes.
to which you can compare that estimate. And if that ground truth exists, then why would you ask a group to give you that?
Yeah, I was wondering who was going to bring this up, especially because I used the word belief on that slide, which is a very tricky term, right? I threw that out there, a little bit of a bait, but also because it's what I'm really interested in. Yeah, so what's an example of a question without a grounded truth? I'm asking you. What's the kind of thing you have in your mind?
I guess, I don't know.
So I don't know, which is better, pizza or hamburgers, right? So we have or like on a scale of 1 to 10, let's put it in numeric. On a scale of 1 to 10, how good is pizza? On a scale of 1 to 10, how good is hamburgers, right? We can do all sorts of numeric stuff that doesn't necessarily have a ground truth. And when we're dealing in the realm of pure opinion, probably no, you're not going to take any kind of crowd estimate, right? I am definitely operating from the perspective that we have some notion of ground truth, but you can get there often by somewhat surprising ways. So maybe it's not a matter of determining once and for all, which is better, pizza or hamburgers, but now I'm going to say, okay, if I were to go survey, citizens of London and ask, we calculate the, score for pizza, score for hamburgers, and take the difference so we know which London prefers and by how much. Now I can have you estimate that number, and there is a ground truth, right? So that's just a way of sharing how I tend to think about these things, and the role of numeric questions that don't have a ground truth is that there's often, a realm in which we're thinking about them in terms of some kind of actual accuracy. But no, if it's pure opinion, then the underlying dynamics here are probably still going to drive outcomes. And I'm going to get in a few minutes into a model of how groups, like how the belief changes over time. That would probably still hold, but we have no way of measuring accuracy because it's
But
non-constant.
then I want to get the word belief then. The example that you gave now is about opinions and like having preferences about a certain things. And the questions that you gave at the beginning, they were more about like information that is kind of objective. So
Yes.
how much will this person perform, let's say in 6 months? So do you make a distinction between those two, or like is your presentation focused then on the?
Well, I'm focused entirely on the belief area because I'm going to be measuring accuracy, right? So I just did nothing. I personally I wouldn't have anything to do with data on people's preferences for different like food choices, except in as much as I'm actually kind of curious now, we would probably find that those follow similar dynamics, right? Because we're sharing numbers. I do want to argue weakly, but I think I could get more confident in this. A belief is always something that can be measured in terms of accuracy. If you're taking a Bayesian perspective, because the belief is something about a statement about the world, so there's always going to be some kind of ground truth, but preferences really hold it. Yeah. Okay. So please, as you continue thinking over the next 45 minutes or hour or so about like beliefs and estimates, and you realize, wait a minute, you forgot this thing. Bring it up because this is really useful stuff for laying the context. Okay, so we've got this background where like research is all over the place about what you do with your group when you want to get optimal estimates. So my answer that I'm going to try to convince you today is not actually a fixed effect. Although this question assumes that for any given group with any given process, there's like a fixed effect, so that if I have a conversation is always either going to improve accuracy or reduce accuracy. Or if I do, the Delphi method is always either going to reduce accuracy or improve accuracy. I'm going to say that's basically not true. And as it turns out, there's a lot of different things that can determine whether or not communication helps increases accuracy. By the way, a little side point, one of the things that always drives me crazy about this research, people want to know how much accuracy increased. You can't really measure accuracy. You can only measure error. That's how much error decreased. But then you get these negative values and people are like, oh, it went down. It's bad, right? Okay, so you're going to see some things going down today. Down is good. But I'll talk you through that when we get there. Okay, so it's not simply a fixed effect. It turns out the outcomes depend on, this is the end, by the way. I'm at the end now. Group process, network structure. So whether they, we already kind of knew whether it's Delphi method or discussion, network structure. So the the patterns of who connects to whom or who observes whom, individual behavioral characteristics, and that's going to turn out to be really important, and then task characteristics. That's going to turn out to be really important in explaining these paradoxes. So this is basically the overview of what I'm going to get to today. Now I'm going to go through and show you this using a little bit of theory and a little bit of data. Okay. Briefly, I want to just give you a bit of a context about the broader world I'm operating in. I'm really interested in collective intelligence broadly. Right now, I'm focused very much on numeric estimate accuracy, but I see this operating within the broader realm of this question of how can we, structure groups and societies and organizations to make good decisions. So the basic principle of collective intelligence is that the whole is greater than the sum of its parts, right? The average estimate of the group is more accurate than the average estimate of some randomly selected individual. But I'm going to push a little further because I'm not just interested in statisticized aggregations, right? That would be what I would call collected intelligence. For me, the magic of collective intelligence really happens when the group is acting as a group, which is somehow other than a purely statistically independent aggregation of individuals. This is just my personal perspective to share a little bit how I think about things, moving from this independent aggregation into groups actually acting like groups. Okay, and then I'm going to breeze through this high level stuff pretty briefly, the kind of levels I'm thinking about. You've got teams of people with similar roles, a lot of academics in the room, we're all basically doing more or less the same thing. You've got organizations, that gets a lot more complicated. You get into division of labor, and then you can get into talking about societies, right? Obviously, opinion emergence in political context is something we really care about. Opinion emergence in health context is something we really care about. Here's where you start to get into really emergent processes. And I tend to operate in the very abstract world. So I'm generally dealing with pretty simple, basic analytic models that, at least in principle, in theory, operate at any of this level. Although, as we get beyond the basic laboratory stuff, some of the questions I'm starting to ask now is, what really matters beyond the basic model. But for me right now, these are all basically the same things. And then when we ask about,
Yeah, so it seems to me that these results very much depend on how the group is constituted, right? Because and how you define the boundaries of the group, because you can have a group of experts or a group of people that has experts and non-experts and so on. So how are these groups constituted?
Yeah, so this is a great question. And actually leads me right into a point I'll answer in a second. I just want to point out that when we start to think about what are the levers we can pull on for engineering collective intelligence, optimizing our groups, one of the big levers we can pull on is group composition. I know that's not quite what you're asking about, but I just wanted to slide into that, which is say, who am I putting in my group? Am I putting all experts? Am I putting a mixture of experts and lay people? If we're predicting, how many papers this job candidate will produce, am I only bringing in, tenured professors? Am I also bringing in postdocs, right? So you can pull on that lever of group composition. You can pull on that lever of group process. These are basically the two things you can pull on. Now, for me, I don't really have to wrestle with those kinds of questions because I'm gonna talk entirely about laboratory studies. So my group is the people, in this particular laboratory study. But in broader context, it would be whoever is contributing that numeric estimate. Yeah.
If you're arguing for the social network before, and now you're talking about a group of experts as something that is kind of artificially assembled, then how are you going to look into the relationship between them?
Yeah, that's great. So again, social networks. When I say social networks, is a great question. Again, I'm going to use the word anemic. All of my models are really anemic. I'm stripping out a lot of the really kind of thick, interesting stuff that makes social life. So for me, when we're going to define an edge in a social network really simply as I observe your answer. That's it. So it's like the Delphi method. We're slipping little numbers around the table. Whose numbers am I observing? That's it. But hold on to that question. If we have time later for some more deeper discussion, I think that's a really interesting topic to explore. Okay. So just super briefly, I want to wrap up the world I live in. So where I situate numeric estimating within the world of collective intelligence, there's a lot of different tasks a group can do. One classic way of dividing up group tasks is in the graph complex. You've got people generating solutions to a problem, choosing solutions to a problem, negotiating solutions, and then executing those plans. nowhere in here really is there room for numeric estimates, except for maybe choosing solutions, but I suspect in reality it happens throughout all of this. So me personally, I divide things up a little more neatly. This comes back, by the way, I used to be a mediator. So I was out of school for a while. I mentioned training customer service. I also worked in mediation and conflict resolution. That's why I think so much about communication and process matters. So we had a 3-step mediation process. Sense making, which I'm now going to call defining the problem. So this is people just sitting around a table talking, kind of getting everything out on the table. Then you got brainstorming. So now you know what the problem is. You're going to list a whole bunch of solutions to them. And then you got evaluation, which I'm kind of merging with selecting solutions, right? So for me in this wisdom crowd, it'd be like, all right, after we've listed all the solutions we can possibly think of, we're going to go through and assign a numeric score. And then of course, pick the one with the highest numeric score. Another very anemic, simplified model of how groups really work. And then, there's also, you can look at it more descriptively in terms of how the research goes. So you've got papers on problem solving that talk about things like navigating the fitness landscape. David Lazar has some really cool papers on, exploration and exploitation of network. You've got creative generation, the whole literature on brainstorming. You've got all this estimation, forecasting stuff. That's what I'm operating in. And then you've got selection in the game theoretic sense. You can think of this as coordination games. I know Doug Gilbo was here last year talking about category emergence. That's a type of coordination, which is essentially a big emergence selection process, right? Where are we going to draw the boundaries for solving this problem of navigating social life, right? So it's a lot more emergent. Okay, so for the rest of the day, I'm going to just dive in now and just stick with estimation or forecasting. So if you have any more like big collective intelligence, broad questions or comments, now's a good time to bring this up. Okay, cool. Let's talk about numbers. Okay, so I mentioned earlier the wisdom of crowds is this phenomenon where the average estimate is mathematically guaranteed to be more accurate than any individual estimate. I want to unpack that a little bit in more analytic terms. So this is an equation. The C here is collective error. So the C here is just the average estimate. So this term here is the collective error equals, so BI is just indexing individual beliefs. I'm using the B here for belief to be a little provocative still. So it's, and that's squared, of course, so this is just summing. So this is collective error equals average individual error minus variance, which is what people often interpret as diversity. How different are our opinions, right? Okay, so this is giving us that mathematical guarantee. Because the collective error is equal to average individual error minus something. So this term must necessarily be smaller than this term, right? And that's it. That's the principle of the wisdom of crowds right there. But this doesn't tell us anything about what social exchange is going to do. This tells us about how our staticized group is going to perform, but nothing about what's going to happen when we start talking to each other. Now, the thing is, people will often draw intuitively from this equation, right? They'll draw intuitively from this equation and say, okay, well, if the collective error benefit is due to this diversity term, right? The bigger we make this term, the smaller we make this term, right? Let's hold individual characteristics constant. We're just going to change the diversity of the group. Okay, so we grow diversity, we hold this constant, we must shrink collective error. So this is what was behind a lot of the stuff like the Jim Surowiecki book and some of the early research really showing social influences. Because they look, it reduces diversity, it leads people to become more similar, okay? But we can actually play around with that and see that that doesn't hold up. I mean, imagine the very simple scenario where you've got a group that's got some C in the beginning, some average estimate. We say there's 100 jelly beans in the jar. And at the end of the conversation, we all agree, we completely converge around that estimate. Well, now diversity has completely collapsed to 0. This term hasn't changed at all. All we have now is that the collective error is equal to the average individual error. So the fact is that it's entirely possible for groups to get better, for groups to get worse, with diversity changing. All these three terms can essentially move independently. There's no like magic rule that says if people become more similar, you lose the wisdom of crowds. Okay, so we're kind of back to asking, fine, then what does determine social influence? Okay, so we've got a nice formal theoretical model we can look at. This is developed by Mars de Groot in 1974. And the model works like this. Each person starts with an estimate. They adopt some new estimate that's equal to a weighted average of peer estimates. So I've got your slip of paper, I've got your slip of paper. Okay, I'm going to maybe give you each 50-50 weight, right? So I'm going to take the weighted average of you two. Then we just repeat that infinitely. You can sort of see intuitively, if we're all sort of revising and adopting each other's weighted averages, we're going to eventually converge asymptotically on a consensus belief. So in fact, asymptotically, variance will drop to 0. And then what that consensus belief is simply an eigenvector weighted sum of the initial estimate. So if you take that, this is defined with a network. As soon as you start talking about each person observing peer estimates, now you've got an adjacency matrix. You take the eigenvector of that adjacency matrix, each person has an eigenvalue. And if my eigenvalue is, whatever 0.03, I'm going to contribute 0.03 to the final weighted group estimate. That holds under pretty basic assumptions, right? You don't want to have completely disconnected clusters in your network. Because, right, obviously, then you're never going to get convergence. So the real key thing here is this eigenvector weighted sum. If you're reading this paper, as I was as a grad student, and you're studying network theory, you're going, wait a minute, that's the name of eigenvector, is just network centrality. So all this is telling us, we're back to, it's really intuitive, but now we have some math to support it. The consensus belief is going to be driven more heavily by the more central individuals in the network. Okay, that's going to turn out to have some subtleties to it. It's going to put a little bit of thickness back in group conversation. Give me a few minutes to get there, because I'm going to start with just some experimental data testing the basic proposition. So if the consensus is simply the eigenvector weighted sum, then all that matters is network centrality. Now that's an individual characteristic, so I'm looking at the group as a whole. We can characterize the distribution of centrality with centralization, which can be measured a lot of different ways. If you're not familiar with that term, you can just use the Gini coefficient. So, if there's a few very central nodes and a lot of peripheral nodes, that would be highly centralized. So we can kind of think about networks as mapping a spectrum of increasing centralization. Over here, we have a nice random network where every person is connected to 4 other people, which in this context means observing the numeric estimates of 4 other people. So I've got 4 friends who I talk to and say, hey, do you think the vaccine is going to work? And they say yes, no, whatever, I adopt a weighted average. But as we move to the right, we get increasingly centralized networks. So we have what's called a star network, where one person observes everybody and everybody observes that one person. So what we should expect now, quiz time. So we start with an initial group average for a decentralized network. After communication, has anybody picked up on what the average in this group should be? The same as the beginning, with that complete collapse in variance and diversity, right? Because this centralized network, everybody's equally weighted and they all have the same eigenvalue. So it's just going to converge on a perfectly unweighted or equally weighted mean of initial estimate. As we move to the right, we get more and more convergent on those central nodes, okay? So I'm going to finally get into some experiments and data now. Thank you for bearing with me with that long introduction. So everything I'm going to talk about today is an experimental test of some version of this theory. And what we're doing, our experimental paradigm, we have people come into a virtual laboratory, so just kind of an online tool. People come in, they all come in at the exact same time because we're doing real-time interactions. They come in, we ask them some forecasting question. I actually have a jar of gumballs in my flat from my dissertation. So you can ask how many jars are in the gumball. We're moving into more interesting questions these days. We'll show people a picture of or a description of a crowdsourcing, crowdfunding campaign. Ask how much did this crowdfunding campaign earn, right? Okay, so they give their initial estimate, then they're going to engage in some kind of social exchange process. It could be discussion, it could be numeric exchange, and then they give a final answer, okay? This is my general paradigm. The first experiment I'm going to talk about really just testing this basic principle of centrality. So we have people come in round 1, they give an independent estimate. Then in round 2, they observe the average, the mean belief of their network neighbors, which we're determining experimentally, randomly assigned. They get to revise their estimate. They don't have to change it. Remember, these are people, they can do whatever they want. They don't have to take the weighted average. And then we give them a third observe and revise. So there's a little bit of iteration so you can get some flow through the network, get towards that asymptotic process. And then we have 2 social conditions. One is a decentralized network. This has 40 nodes. We've got 40 people coming in simultaneously. or more often, or we've got a highly centralized network, one central node and 39 peripheral nodes, so 40 people total. I'll tell you now what I wish I'd done differently in this study. Because what I wish I'd done is had it such that everybody was observing the central node, but that the central node was observing everybody, but I wish I had not made it a symmetrical network. Because right now we have a huge difference between like in degree and out degree centrality. You always think of better ways to run your experiments. So, okay. And then we want to know, we want to separate the effective revision from the effect of social influence. You give me 5 minutes with that jar of jelly beans, I'm going to start counting them, right? So we also have a control condition where people are answering the questions 3 times, same exact amount of time. The only difference between the control condition, social condition is there is no social information. And importantly, people in these 2 social conditions have the same exact experience. They have no way of knowing what network they're in. They give an estimate, they see an average that they're told is the average of their peers, and they revise. Okay. Yes.
Can you clarify the difference between social influence and revising the estimate? It sounds very much.
Yeah, basically, yeah. So social influence is something I'm doing to someone else. Revising an estimate is something I'm doing in response to social influence. Yeah.
Okay.
Just to confirm, in the centralized condition, so is the node in the middle, is that person going to get a giant list of other
In
people?
this study, we are only showing the mean estimate for that very reason.
Gotcha.
That would be crazy, which is why I now wish I'd done the asymmetric networks would have given me a little more flexibility. These days, I'm trying to loosen things up a little bit, so I'm showing the list. But so I'll do that in a later experiment. More or less the same results.
Okay.
But there's probably some subtle differences, right? They don't seem to be important yet. I see this whole project as starting with trying to like refine down like a wood carving. We start with just like, we need a block of wood, and then we're starting to try to carve shapes out of it and getting it smoother. So, okay. So for this experiment, I first wanted to show you variance. So you can't really tell because they're totally overlapping. The blue line is decentralized, the pink line is the centralized network. As we go from round 1 to round 2 to round 3, variance is decreasing, or I'm measuring standard deviation, right? So and it's the same for both decentralized and centralized networks. Totally different structure. They're becoming increasingly more consensus. But if we look at the change in the error itself, I was going to invite you to make predictions, but nobody seems super forthcoming with their answer. To anybody have any predictions? It's okay if you're wrong. What do you think the decentralized network is going to do? That's the real question. What?
The error would decrease.
Yeah, that's pretty good. So surprisingly, we didn't expect this. Remember, decentralized network, we expect to converge right on the mean. Turns out the decentralized network is reliably improving. Decrease in error, down is good. We're measuring both the mean and the median, primarily because reviewers were asking. I have no theory about the median, because the DeGroot model is all in the mean, and these are not symmetric distributions. Okay, but when we look at the centralized networks, well, we're not just going to ask what does the centralized network do, because it's entirely determined by the central node. So when we look at the case of the centralized person, say I'm the central node, if my belief is in the direction of truth, the group's going to get more accurate, less error. When I'm away from truth, the group's going to be less accurate. Now, this is important. It doesn't actually mean that I'm accurate. I can be in the direction of truth without being accurate. If the crowd answer is 90 and the true answer is 100 and my answer is 1,000, I am wildly inaccurate, but the group moving towards me will, by coincidence, really move in the right direction. So there's no systematic benefit or risk of centralized networks. Depends on the direction of the central node. There was a hand.
Yeah, I was just going to say in the experiment, when you don't separate these by when you're not stratifying by what the centralized node is giving you as an answer, does it typically wash out? Is it going to be negative? Is it going to be positive?
I honestly don't remember, but it's not really a meaningful question to me to ask, because it's so, intuitively and in the results, it's so obvious that you have 40 people looking at one person's answer. We really kind of teed the ball up on that one, right? But we're trying to get the basic effects. So I don't know, those bars look about the same, probably washed out, but we don't know that these are equal sample sizes. Yeah.
It's okay. I was going to ask if the central node is getting closer to the truth
Yeah.
in their prediction.
So you're asking about the movement of the central node
Yeah.
itself? Yeah. Sure.
Because that node is actually getting information.
Yeah, so if we're talking about we're a long-term. So what I'm basically saying, yes, this is a kind of long asymptotic dynamic process. The claim I'm making is that it's the starting points that are basically going to predict the trajectory of the group with a usefully high degree of certainty, right? There's going to be edge cases as you dig into the data. Yeah.
I'm still struggling to understand kind of like what the purpose is, especially of the centralized network, because if I understand it correctly, you're kind of like in this decentralized network, you have this idea of diversity, and your idea is kind of like you can ignore diversity, but isn't the centralized network kind of like still going back again into like this individual estimate rather than kind of like a group estimate?
So I call centralized networks the wisdom of the few, because it's not only, sometimes it's a few central people, but like if you have a few central people in a large group, you're exactly right. They're going to determine. So in expectation, we could show empirically it's fuzzier. In expectation, we can show mathematically that centralized networks will systematically decrease error compared with decentralized networks, because it's just higher variance on the final estimate than compared to the beginning estimate. That's a little different than empirically though, because it turns out whether this central individual towards truth or away from truth is to some extent a characteristic of the estimate distribution. Yes.
Did you run the experiment with people knowing about being either in the centralized network or non-centralized?
They were completely blind. All they were told is, here's some information from other people in the experiment. Or I don't remember the exact word. Okay, I want to highlight really two. This is kind of straightforward. Well, the centralized stuff, nothing should be surprising here. Decentralized network is a little surprising. I want to highlight two things about this that I'm going to move forward with. One is that this notion of the centralized individual being towards or away from truth, right? I just want to highlight that because that's going to come back and turn out to be really important in understanding things like group conversation, the more informal interactions. The other is this improvement here. We've got decentralized networks appear to be reliably improving. I'm going to complicate that reliably later because it doesn't always show up in the data, but at least in this experiment, in this group with these questions, reliably improving. Yeah.
Yeah, this is a sort of follow-up on that. I was wondering about this with any of these sort of eigenvector things where you have this kind of idea of an infinite regress that you're modeling. Have you tried the experiment with more than 2 rounds of revision? Does it seem like it continues in that direction?
I have not, at least not in any systematic way. I mean, it's a cost issue for one. You know, I try to pay MTARCs very fairly. I would suspect that people are not asymptotic, that eventually I'm going to stop revising my answer, right? Because 100 rounds into it, and be like, what the hell is this experiment doing with me, right? So this is where, you know, moving from the laboratory into real world problems can be a little bit tricky. So I'm going to postpone those kinds of discussions towards the end, but by the time we get to the end, we'll have a little bit more fodder for thinking through more natural interactions. But in terms of explaining why are decentralized networks improving, we have to remember that when it comes to centrality, I'm not only placing weight on other people's estimates, I'm also placing some weight on my own estimates. So if we actually look at the adjacency matrix, we just say we've got a group of 5 people, you know, P, 1, 2, I use a P for persuasiveness, you know, 2 is persuading 1, 1 is persuading 2. Well, you've also got this S, I'm going to call either self-weight or stubbornness, whatever you want to call it. I'm going to take maybe 30% of one estimate, 30% of another estimate, and 40% of my own estimate as I'm making my weighted revision. So it turns out even in a network that's perfectly decentralized from a binary edge definition of who observes whom, it can be centralized to the actual weighted influence network, and I can become more central simply by being stubborn. So if we take, and again, I don't think this would happen in the lab, but if we take the asymptotic case seriously, let's say we have a group of 5 people, I am completely stubborn, I place 100% on my own belief. I'm basically never going to change over time. But asymptotically, other people are going to slowly revise towards me. So asymptotically, my stubbornness is going to essentially lead the group to just adopt my estimate at the end of the day, the wisdom of the few. So what's kind of exciting to me and what I'm going to be basically talking about towards the end is, how this emergent centralization in unexpected ways can drive outcomes. So then this was my dissertation, and I went around for a while saying, okay, cool, well, just have people communicate numerically in decentralized networks, and it'll reliably improve accuracy. And then, I realized, so this is a caveat. I'm not going to get into this too much as a piece for another day. I just want to give a caveat. Beware of binary choice. Remember that the group model is all in the continuous spectrum of numbers. But if at the end of the day, let's say we're doing numeric estimate, how many jelly beans are in the jar, right? That's going to follow the group model. But now we say, I only invest in jars with more than 100 jelly beans. So my decision, which is say what I want you to forecast, is really, does this jar have more than 100 jelly beans in it? It turns out, and this is just one of those weird numeric paradoxes, you can have a group, one in the same group, one in the same conversation, the same vector of estimates, where the average estimate becomes more accurate, while the percentage of people with the correct thresholded choice, their vote, what they're going to do, decreases. So the vote becomes less accurate, even as that wisdom of crowds becomes more accurate. That's why I say beware of binary choices. This doesn't apply when you have people taking a vote at the end of the day. Okay, that's my caveat. And I love this stuff, so I'm more than happy to go back into this later if you want. Okay, so I'm talking about this kind of emergent centralization. Pay careful attention to people, whether or not they're towards truth or away from truth. So we can kind of characterize that systematically in terms of a belief distribution. So let's say I go around and I have the same jar of jelly beans, and I'm asking people how many jelly beans are in the jar. That's a pretty stable distribution, that task, right? And I can characterize that, this is totally hypothetical, but I can characterize that based on the percentage of people who are towards or away from truth with respect to the mean. This is important, so I really want to stick with this, ask questions about this, make sure you understand this. So I'm saying that this is, we can characterize any belief distribution, given a belief distribution, given a ground truth value, the belief distribution has some mean. There will be some percentage of people on this side of the mean and some percentage of people on that side of the mean. So if we were to, this is an example of 20% towards. So now we can get back into that systematic behavior of centralized networks. If we were to run a centralized network experiment over and over and over on this distribution, it would improve 20% of the time, right? Because 20% just in expectation. If we were to use a flipped distribution, it's hard to find long tail to the left, but let's say we had a mirror image distribution, which was 80% towards truth. Well, then we would expect it to improve 80% of the time. So there is no fixed effect for centralized networks. It turns out that the effect of centralized networks depends not only on the process, but whether or not it depends on the task characteristics itself. Yeah.
I'm still not sure I follow with regard to this towards in a way, because basically, isn't this kind of like this two-sided problem where the truth is in the middle and you can place estimates on either side? So that kind of like the idea should be to get the mean of to get kind of like the distribution to peak on the truth. Kind of like, so how does the toward and away be like on these two sides?
Yeah, so right now I'm trying to say something purely descriptive. This is not prescriptive. I'm not saying anything you do anything with yet. I'm just saying this is simply a feature of any estimate distribution. Give me an estimate distribution. There is a defined mean and there is a defined true value. So I'm just saying you can characterize that estimate distribution in terms of the percentage of people on the same side of the mean as the true value.
Okay.
So just given any estimate distribution, you can characterize it with a percentage.
So basically 80% are on the one side of truth and 20% on the other side of.
This is an example, it could be any percent.
Yeah, but and then away and toward means like where's the mean, and the mean is always on the away side.
Yeah, so I could, there's no Marcus here, but I could ask another question where the truth is over here and the mean is over here, right? There's nothing fixed about this, but give me a task. I was just going to draw more line. So, just to vary it up, we're asking different questions. Instead of jelly beans, we're asking about, the value of some company, and now I've got a completely different distribution here. I know it looks a lot similar. Let's say the true answer is, it's worth $1 million. But this is a super long tail distribution. So now the mean is over here, and now we have something like, 80% of people are on the true side of the mean. Whatever it is, give me any distribution with a mean and a true value, and I can tell you the percentage. It's just a way of characterizing distribution.
But the one that is away is the one that is closer to the mean.
Say what?
The one that you name as away from the truth is the one that is on the side of the mean.
So if the truth is here, I can be right here, which is very close to the mean and away from truth. Or it can be right here, which is very close to the mean and towards truth. Is that? I don't quite understand what your question is.
I think we're confused with the terms away and towards the truth.
Yes, it is. Yeah, that's why I'm sticking with this. All right, so let's say your estimate is here, right? Well, sorry, remind me your name.
Rodrigo.
Rodrigo. Let's say your estimate is here. You would be on the truth side of the mean. Do you agree with that? Because the mean is here, the truth is here, and you're on the same side of the mean as the truth.
Okay.
With this shape, 20% of the people are in the same camp as you. But if Carolee, am I saying that? Yes. If Carolee, thinks it's really low, Carolee's going to be on the opposite side of the mean from the true value. And 80% of people are over here. So give me, so you can place people anywhere, but because this is, I'm assuming, a large distribution, this assumption, it's going to be a stable characteristic of the task. So I can say this is a task that generates a distribution with this characteristic. If you don't, I'm going to move forward, but bring these questions back up as I get into it, and maybe some of the context will help, but let's make sure you get this as we move forward. Okay, so my hypothesis is that this percentage is going to predict whether or not centralized networks improve. Okay, and I actually realized as like an hour ago as I was prepping for today, I'm sorry, I never measured this for the centralized networks in my dissertation data. I didn't think about it today. This became important to me because I was thinking about conversation. I'm sitting in a lab meeting one day, and some people are talking a lot more. I'm a talkative person. Some people are talking a lot more than other people, right? So I'm starting to think like, okay, a conversation, if we were to look at it in a binary network, who observes whom, it's a fully connected network. Everybody here observes everybody. There's nothing interesting about that centralization. But if you look at who talks and how much, it becomes highly centralized, which means a simple conversation should be predicted, whether or not that conversation is helpful, should be predicted by this value. Whether, what percentage of people are toward or away from truth should predict whether a conversation is helpful and harmful. So it also, this is the same kind of emergent centralization, by the way, that lets stubborn people be more influential. But one of the interesting things is that stubbornness, it turns out, correlates with accuracy. And that's why the emergent centralization through stubbornness tends to reliably improve decentralized networks. I'm not going to stand here and say that will always happen. I'm going to say that's been true in some of the empirical data. I'm going to fail to replicate that in some new data. So that's yet another characteristic. The correlation between confidence and accuracy is going to determine a group behavior. This centralization of talkativeness is going to determine a group behavior. And basically what I'm going to do is I'm going to try to prove that point by measuring outcomes for group discussions and showing that this characteristic predicts them. Okay, there's a hand. Yeah.
Right. When you said like the stubbornness correlates with the accuracy, do you assume that stubbornness is constant over time, or does that change?
I have no opinion on that. Yeah. So
like if someone is stubborn but still gets a signal from the population such that it's like that person's accuracy is getting further and further away, maybe the stubbornness goes down.
Could be.
It's through social influence, right?
Again, as soon as we get into like asymptotic real human results, I would be largely speculating if I were to answer. So I'll just say that what I measured was how much did you revise your answer? So I'm looking at behavioral stubbornness. That turns out to correlate with error. But there's also some of these data sets, people have confidence, and you can go back and measure the confidence, self-reported confidence. That also turns out to correlate with error. And these two things also correlate with each other noisily. So how stubborn I am is only somewhat correlated with how confident I am. Go figure. Turns out, though, talkativeness does not correlate with accuracy. I'm just going to tell you that right now, okay? That's a preview. And here's my intuition for that. If I have an answer, if I have an estimate, I've got some sense of how confident I am, and that's going to determine my adjustment, right? I'm making some decisions there. I am just a naturally talkative person. I'm Jewish, I come from a very large family, and I'm American. So that's like a, trifecta. I talk a lot. And if I cut you off before the end of your sentence finishes, please don't take it personally. It's just how we do. But that's a stable characteristic of me, more or less. Even when I'm less talkative, even when I'm feeling shy, I talk more than most people. So I go into a conversation about something I know a lot, I'm going to talk a lot. I go into a conversation about something I know very little, I'm going to talk a lot. So that's why I think the talkativeness is more problematic than the stubbornness. But that's, to be determined. That's a sort of a future research thing. Okay, so I'm going to try to prove that this predicts outcomes in discussions. I'm going to do that with sort of two collections. One, and this is, I tested these ideas on a reanalysis of previous data sets. So this is the one by Lorenz et al. This is my dissertation, the one I showed you. This is another one I collected that was methodologically the same as my dissertation, but on political beliefs. These are all numeric exchange. So I've got 3 numeric exchange data sets, got 1 discussion data set. This is out of, this is like this is Phil Tetlock's group, Barbara Miller's, Phil Tetlock, Pavel Atanas, the good judgment people. Okay, so, but this doesn't let me directly compare numeric exchange and discussion, right? It's across paradigms, across researchers. I'm going to do that anyway, but I'm also going to replicate this whole thing. So I'm going to run 100 trials with numeric exchange, 100 trials with discussion. I'm now going to drop to 20 per group. I don't really need 40 people. I want enough for some emergent centralization, but small enough that you can have a real conversation. Okay. And I'm asking kind of thicker questions here, something to give them something to talk about. So I'm not doing jelly beans in a jar. Now I'm doing the how much is this crowdfunding campaign going to earn type questions. I think I asked, what was US military spending as % of something? I spend a lot of time looking for stuff that's hard to Google, basically hard to Google, but kind of interesting and something I can find the true answer to. So basically for this experiment, I've only got 2 conditions. I'm dispensing with the control condition now. I only want to compare discussion and numeric exchange. So people come in and I'm basically randomizing them. I actually pre-randomize. So what I do is I recruit people, the panel, I get like 15,000 people on MTurk to just say, yes, I would like to participate in research. And that way, if you've used MTurk, once they complete a task with you, you can now email them. So this is how I get lots of people at once and send them all a link and say, hey, click this thing right now. And we've got a bunch of machinery. So I'm pre-randomizing them. So running discussion and numeric exchange separately for my own personal sanity. Okay, so now what I'm going to do is I'm going to take the data from the discussion. I'm going to take the data from the numeric exchange, and I'm just going to plot the probability that they improved as a function of the percentage towards truth. Okay, and I'm going to call that phi. I don't remember why I came up with phi, but phi is probably because it's just a p like letter. Phi is the proportion towards truth. So if we look at this chart, 50%, the midline would be neither improving nor getting worse systematically. 0 means they're always getting worse. 100% means they're always getting better. And then phi is on a spectrum from 0 to 1, percentage of people on the true side of the answer. And if we look at numeric exchange, the Delphi method, we do see some effect of phi. Remember that emergent centralization from stubbornness, but it's weaker, okay? So there's an effect of this proportion for numeric exchange, but it's weaker. Why is it weaker for numeric exchange? This is because, well, there's only so much I can be influential by being stubborn. If I'm stubborn, I change my own behavior and other people revise towards me. But if I'm really persuasive through a conversation, in one fell swoop, I can get everyone to adopt my belief. And I glazed through it. I'm sorry, this is all pre-registered hypotheses and tests and everything. because I did all this on the reanalysis of previous data. This is everything binned together with a logistic clustered regression with random effects for data set, basically, okay? So I find that Delphi is somewhat impacted by this proportion. Discussion is hugely impacted. There's a much bigger effect. So when we look at the logistic regression, the slopes on each of these lines is significant and the interaction term is significant. So we have reason to believe that this is a real effect. So this is doing a lot for us right now. One is it's confirming this intuition that there's some kind of emergent centralization that's interacting with task distribution. So if I come to this group and I say, let's have a conversation and see if our wisdom of crowds becomes more wise, whether we talk about jelly beans or whether we talk about, market forecasting, we could get completely different outcomes. In jelly beans, maybe our discussion is really helpful. In market forecasting, maybe our discussion is really harmful. It has nothing to do with us. It's a statistical artifact of that pre-discussion belief distribution. So that's one really big takeaway here. Remember, I said, I don't believe there's a fixed effect of communication. This is a big part of why. We can also now unpack those contradictory results from previous research. Remember, I started by saying, look, if we look at previous studies, some say independence is best, some say communication is best, some says discussion outperforms numeric exchange, some says that numeric exchange outperforms discussion. So we can now explain the contradictory results in this previous research as essentially previously unspecified variation in this parameter space, right? So I can't say this for certainty because I don't have the data from all those studies in the 60s and 70s, but it's entirely possible that one study finding the benefits of discussion was simply asking different questions than one study finding the benefits of the Delphi method, okay? Now, I said that I was no longer as confident as I used to be about the reliable benefits of the Delphi method, numeric exchange. And this is why. I claimed that in my dissertation, people reliably improved because of this stubbornness, accuracy, correlation that interacts with the diagonal and the group model, but it may very well have been that we happened to select tasks from this side of the distribution. So that's kind of the punchline. There's one point, I binned a bunch of data together here from different studies, just so you know I'm not making stuff up. This is just the data from the reanalysis. So these are actually completely different experiments, these two lines. This is the data from my replication. And also when you look at the numbers in the logistic regression, it's actually kind of surprising how similar the effects were. This has got to be some statistical luck here too. Just fortunately, this line looks a little bit off, which makes me feel better. By the way, this is a line from those previous studies showing the reliable improvement. In this study, we worked hard to get more of a distribution of phi. Yes.
It's very hard for me to think of the Delphi methods as something outside of a theoretical model. Can you give an example of an application?
An application
Or like
of people using the Delphi method, or how I would do it in the laboratory?
How people are like real life.
Yeah, so the answer is going to be the same. How I would do it if I wanted to apply it would be the same as a laboratory. So I would say, if we want to forecast something, I'd say, okay, everybody, write down your answer on a piece of paper, or we would use like an Excel spreadsheet or some kind of, we could use my like virtual lab tool. We would all write down our numbers. We would all see the average of the group and we would revise. So it's something you can implement very simply in any setting. And, the Delphi method, there's this is kind of a weird academic thing. There are an enormous number of papers writing about and using the Delphi method for forecasting. There are a very small number of papers like this. I basically listed every one today because it's all I could find, actually testing them. So in practice, I want to caution, and I actually try not to use the word Delphi method anymore. You'll notice that I did use a label. I'm trying to move towards the numeric exchange because in practice, it's kind of like neoliberalism. People use the word in very different ways. So sometimes people have you write down your why you think that. So your number in one supporting argument, right? So there's a lot of different various implementations. What I'm trying to get at is the basic kind of underlying dynamics of numeric exchange, just the numbers, versus how we talk at the table just to start. Eventually, I want to build back up to all that, thickness of real life processes, but I'm still dwelling very much in the laboratory. Okay, so I want to make one final point to convince you that this fee is really what's going on here, and that it's a result of emergent centralization. So what I can do, if it's really emergent centralization driven by talkativeness, I should be able to go to my chat transcripts, count how much each person talked, calculate who the most talkative person is, and ask, is their answer in the direction of truth or not? And see if that one most talkative person predicts group outcomes. And they do. These error bars overlap, but in the proportion test, this is significant. So I've here separated my replication, my reanalysis data. This is just discussion. This is just one study each panel. Because remember, there was only one previous study with discussion data that I could get. So what we find is that when the most talkative person, I'm calling it central node because it's perfectly valid to define talkativeness or centrality as talkativeness. When the most talkative person is in the direction of truth, the group gets better. When the most talkative person is away from truth, the group gets worse. So this is by no means like proof, but this is just showing that under the hood, the mechanisms are consistent with what we expect. And I want to share one final point about proof, by the way. None of this stuff with phi is strictly causal evidence because we are not randomly assigning phi, right? So we have to be careful about causal interpretations here. We have a strong theoretical model. We have observational evidence that's consistent with our hypotheses. We have this, mechanism evidence that's consistent with what's under the hood. But it could be, hypothetically, let's suppose that people who give very large answers are somehow systematically different than people who give very small answers, right? That's absurd, but it's just a thought experiment. Then a distribution with a high phi, because that's the proportion of people above the mean, is going to be different than a distribution with low phi in terms of the number of people with large answers. So we can't experimentally control this in any randomized controlled trial sense because we can't assign estimates. It's kind of like saying, I believe H distribution matters. I can't assign a group to have a particular H distribution. So we're triangulating here from theory, observational evidence, and mechanisms test. Okay, so that is my median punchline, is that the wisdom of crowds is kind of fragile, right? When it comes to communication, it can help, it can hurt. You don't really, this is kind of upsetting because earlier I could have just said, oh, no problem, just do a decentralized network and have numeric exchange and you'll benefit from the wisdom of crowds. But now I'm going to stand here and say, I actually cannot predict in advance because it depends on whether you're talking about jelly beans or stock market forecasts. I don't know. So that's kind of where I'm at right now. One direction I kind of want to go with, if I can figure out how to get it off the ground, is just like testing a whole bunch of different topics to sort of get a sense of the estimate distribution. I actually have no idea if this is like a stable feature of the task, right? Because in a sample size of 20 people, obviously there's just going to be huge variation in the distribution anyway, right? So I'm not quite sure what to do with this, but from a theoretical perspective, in terms of understanding how groups work, this is, I think, really exciting. I am a management person and a person who was working in the world before going back to academia. So I'm always keeping a close eye on how to develop tools or processes that we can use. I would say right now, hedge your bets and go with that independent aggregation, but it's kind of hard to say. But this is all for the crowds. I'm going to give you a really optimistic closing, which is, this is a project I'm working on right now, but basically the wisdom of crowds is really fragile for the group. It turns out that communication has incredibly robust benefits for individuals. So again, let's go back to this equation. I've taken the math out now, just put the concept in here, but I've rearranged the terms a little bit. Now I'm saying average individual error equals collective error minus diversity. And as we shrink this diversity term here, now we have people becoming more similar. Let's hold the average estimate constant. Well, there is something wrong with this equation. Yeah, this needs to be a plus sign.
Right.
Yeah. So As you shrink diversity, average individual error will also get smaller. So all of this worrying about losing variance turns out it's really good for the individual. And this is super intuitive, right? If the average answer is guaranteed to be more accurate than a randomly selected individual, then collapsing around that average answer, of course, is going to improve individuals and expectation. So this is just one, thought experiment, one scenario. As diversity goes to 0 and average error remains constant, and then this is a plus sign, average individual error will shrink. And that's similar, if the group just converges on the mean. So now I want to ask, how robust is this benefit for individuals? This is in the case where we all converge on the mean. Again, that decentralized nice control condition. I want to look and see, what about centralized networks? What about when the group as a whole gets worse? Can individuals still improve? So I'm going to do this through 2 theoretical models. One you've already seen, so I'm just going to make more hay out of the group model and think through some of the implications of that. One is just like a stupidly simple information exchange model I came up with just to think through some of the implications. And I'm going to reanalyze the data I've been talking about, but instead of looking at group outcomes, I'm going to look at individual outcomes. I know we have about 20 minutes left. I don't know what your norm is here. Can I just kind of keep, oh no, can I just keep going, or should
It's up to you.
All right, I'm just going to keep going. This is pretty much the last piece. So in the model 1, you've already seen, just a reminder, each person forms an opinion, you observe your peer, you update his weighted average, you rinse and repeat. So we can simulate this because that's easier than thinking through the math, and we get some nice figures. So this is a range of outcomes. I'm testing centralized networks. So I've got networks going from perfectly decentralized to perfectly centralized. I've got groups where I'm messing with the correlation between stubbornness and accuracy. Because remember, that correlation between stubbornness and accuracy was important to groups improving. Let's see how important it is for individuals. And I run my simulation. So when the group has really low error, which is to say the average is initially accurate, any change is necessarily going to make the group worse, right? Any change is going to make it worse. So you can never really get a negative here. So the correlation, when it's negative, the group gets worse. When it's 0, the group just converges on the mean. It's not getting worse. For centralized networks, when they're low error, any centralization systematically makes the group worse. When it's high error, a little bit of centralization helps. A lot of centralization makes things worse because you got that variance. Okay, so this is basically what we expected from our previous stuff. Now, if we look at how individuals fare in these groups, we get much more optimistic results. So basically, in the case where the group is initially accurate, and we always get individuals improving across the whole spectrum, this is where the stubborn people are wildly inaccurate. Individuals are still improving, right? When you have really high error, it breaks down a little bit. So I'm not going to stand here and say individuals always improve. There are regimes. If you have a super negative correlation, so that stubborn people are wildly inaccurate, then individuals can get worse. But for a wide range, including some of that negative area, individuals improve. And I would be very shocked if you find any empirical data on the extremes of that stubbornness accuracy correlation. But it could happen. This is important so that we don't say anything and say individuals always improve. We can just say they often improve, and particularly they improve under scenarios that make groups worse, right? And then when we look at centralized networks, well, the individuals across the spectrum are improving in centralized networks. So now we have cases where centralized networks are more or less reliably hurting groups, but individuals can still benefit from them, okay? Another model I was using to think through, everybody begins with a random signal. This could be something you read in the newspaper. That signal is essentially a number. I read a newspaper, it tells me there's 100 jelly beans in the jar. My estimate is the average of the signals I have. I start with one signal, but I can accumulate signals so that each time step, we're going to randomly select an edge of the network, and the 2 nodes are going to share their information. It's like, I read the newspaper, you read the newspaper, what do we think? And we can plot how group accuracy does over time. In the asymptotic case, these groups will end where they start. Because the initial scenario, everybody has a different signal. The crowd average is equal to the average of signal. At the end, if we're swapping information, eventually we're all going to have all the signals. every individual answer is going to be the average, which means the group average is not going to change. But there's some in-between regimes. So mostly looking at short-term outcomes. But I have a little panel that shows long-term outcomes. So over the short term, we start with the group that has initially the group itself is accurate. Any change is going to be bad. And the reason that information flowing makes the group worse is because initially we have a perfectly unweighted average of signals, but as soon as I share a signal to you, that signal is now double counted in the group average. So we have this non-monotonic effect where asymptotically the group ends up where it starts, but in the meantime, the group is getting worse. Now, individuals, I don't even need a simulation to think this through, right? If I'm an individual and I am gradually getting more information, then I'm essentially gradually converging my own belief on the average of the full information state. So individuals are monotonically improving both in the short term and asymptotically. So this is just a thought experiment because I wanted to think through what if we're not using the group model, that simple number exchange model? What if we're using an information model? Even in the information model, individuals are still getting better when the group gets worse. So now basically I'm going to go and I'm going to analyze. These are all the data sets I used in my previous reanalysis. I haven't moved my newest one into this project, so I assume it would be more or less the same. So I'm just going to show you a bunch of plots that summarize what's going on. And the moral of the story is individuals can get better even when groups get worse. So we look at the centralized exchange networks. Individuals get better. We look at the decentralized exchange networks. Individuals get a lot better. We look at open discussion. This is not my data. This is the Good Judgment Project data. Individuals get way better. We look at no social signal at all. Individuals get nominally better. That's not significant, but okay. We're not surprised that people get a little better when they spend some time counting jelly beans, right? Okay, so that's the big picture. These are all the parts of the parameter space that will make groups worse, and they make groups better. But we can now even condition outcomes on the question of did the group get worse? So if I have a group that got worse, what are the fate of the individuals for that particular group? By condition outcomes. So these are now same colors as on the left. So purple is the centralized exchange. When the group got worse, individuals are still nominally getting better, but it's not significant. So at least here we can say when the groups get worse, individuals are still doing all right. And when the groups get better, the individuals get way better. And then this, I'm not going to go, I'll share these or we can show these slides. This just breaks it down and shows that it's more or less the same for all the data sets. I do have one data set where the individuals got worse when the groups got worse, but we're always going to expect a little bouncing around. Okay, so there's one last question you should be asking. What about the best people in the group? If I know I'm an expert, or I believe I'm an expert, should I bother talking with all these people? They're just going to drag me down, right? So this is a tough question. From a practical perspective, this is a tough question. Do you really know if you're an expert? We already saw that correlation is, the confidence or stubbornness is correlated with accuracy, but it's loosely correlated. So is it correlated enough for you to be sure you're in that top 1%? So what we can do is this is a little bit tricky statistically. I'd love some better ideas for this. What we can do is we can basically group people into quartiles on their error, right? And look at where the people in the lowest quartile, the highest quartile, did they get better or worse? Now there's gonna be a regression to the mean here. If I randomly select someone who's really bad at time 1, that's a purely random process, then by random chance, they're gonna be close to the average at time 2. So here, comparing is the control data where people don't have social influence becomes important. So all the experiments I'm looking at in this one have control data. So this is a lot of information, but it takes those quartiles and looked at it. I separated it for all of the different studies. And basically what it shows is that let's take this panel up here. People all the way on the left are the people who were initially most accurate. Yes, people who are initially most accurate are nominally getting worse. It's exactly what we expect from regression to the mean. But look at this gray bar here. That's the control condition. They are nominally getting the most worse. So in Becker et al. 2017, even the best people, they may have nothing to gain from discussion, but on average, they're not going to lose anything. In this study, they appear to be nominally getting worse, but it bounces around a bit in this study. No risk to being expert in discussion in this study, nominally worse. So kind of across these, we basically see if you're in the initially most accurate quartile, you have nothing to lose. So unless you're like really confident, which I find somewhat implausible, I would say participate in the discussion. If you're making an individual decision, remember, I'm now only talking to the point where I'm gonna like go back to my desk and make my own private investment decision. And organizationally, my investment decision is independent, right? If it can come back to averages at the end in any way, you want to steer clear of this kind of argument. Okay, so that is everything. So what I talk about today, social learning is very robust for individuals, not so robust for groups. For groups, there's no simple fixed effect. We've got network structure, we've got task characteristics, we've got people characteristics, whether or not accuracy is correlated with stubbornness. You can imagine that varying from organization to organization. Maybe you've got one really well-calibrated organization, one really poorly calibrated organization. And then just be careful because all of this falls apart if you get into this binary choice voting type stuff. Thank you.
Thank you so much, Joshua.
My pleasure. Yeah, so I'm sorry, I've been totally not seeing the hands up.
They're now just uploading. I've been following.
Oh, you
They're
have?
uploading
Okay,
now.
cool.
Yes. So if there are any questions, we have about 15 minutes or so.